In this video, we are going to talk about transformation between Cartesian coordinates, and we'll be using regular mathematical vectors so that later in our following video, we can generalize to other tensors other than just vectors. This here is our overview slide, which I'll spend about 5 minutes on before I go into each topic in more detail and with examples. The first introductory statement I'm going to make actually kind of is a preview of our next video, which is that this tensor notation here, where we have the t with the double bar, and we write it with the indices I, j, and k, and then our bases, will make it easy to transform tensors between different coordinate systems. So in this chapter, in this video, only transformations between orthonormal systems are considered. Later, in a much later chapter, there'll be other non-orthonormal systems. So first we will look at vector transformations between Cartesian systems, and this whole video is about Cartesian systems. And the first transformation we will consider is a rotation, and that is a prime system is rotated by an angle theta with respect to an unprimed system. And our matrix for our transformation is this one here, which has the column vectors cosine theta minus sine theta, cosine theta. And the idea is you could take a vector from our unprimed system, our original Cartesian coordinate system with standard bases, and then you can get our new vector v prime, which is in the coordinate system rotated, our standard bases rotated by an angle of theta. So we'll go through how this is derived. Our next topic will be finding the transformation, our a sub ij, when we're going from a vector coordinate system v to a different primed vector system. And we'll go over two methods for finding the transformation matrix, and the choice of which one to use depends on what information you have. First will be the basis vector transformation. So the bases of both coordinate systems are known, and we'll use this formula here that we have seen in linear algebra, but also using our index notation, we're going to find this formula here, which is a much faster way of finding this matrix. The next method is to determine the transformation matrix from the coordinate equation. So if the basis vectors are not explicitly known, but the coordinate equations relating the two systems is known, then we have these formulas here to find the transformation matrix, and we'll do an example of that. And then finally, because we're focused on orthonormal systems right now, we have this orthonormal property of our matrix and the inverse, and what it turns out is the inverse will be simply equal to the transpose of our matrix, which makes it very easy to find the inverse matrix for the to transform matrices vectors from our primed system to our unprimed system. As I had mentioned, in this video we are going to be talking about vector transformations, the ones that we are pretty familiar with from linear algebra, but we will extend those notions in the next video to general tensors. So they'll be where our tensors can be matrices or arrays of matrices or arrays of matrices. But for now, we're going to start with vectors. And we'll start with this first transformation, a rotation. Our first example will be a rotation where a primed system is rotated by an angle theta with respect to an unprimed system. So here is our unprimed system. It's just going to be our standard bases. So here's E1. Let's just say that this is scaled, so 4 squares is 1 unit. And here's E2 hat. And then over here is our primed system, which is achieved by taking the standard bases and rotating by an angle of theta. So the x-axis is rotated by an angle of theta to get our new v1 axis. And then our v2 axis is taken by rotating this y-axis also by an angle of theta, or the whole thing is rotated by theta. And this is actually our matrix that will achieve the transformation of vector v1. So if we know the coordinates of v1 in our standard basis, in this case we can see it's equal to, and remember, if this is 1, then this over here is 1/2 1. We can plug in 1/2 1 into here, cosine theta, whatever our degree theta is. In this drawing, theta is equal to pi over 4, and then we can find the coordinates of this point v in this new coordinate system. But let's see how we get this matrix. Also, to start with, for your reference, I drew this unit circle. Since this basis here, the standard basis, is simply rotated, it's not stretched or lengthened or contracted, that means my new basis here will be the end of my next, where the vector 0, 1 ends up at this point, and this vector 1, 0 will end up at this point. The next thing I'm just going to draw is for my point V, perpendicular to my first axis, that's going to be my first coordinate. And remember, if this is unit length 1 here, that means in this direction, in the x direction, it's 1/2. And over here in the y direction, the coordinate in my standard basis is going to be 1/2 and 1. Similarly, if I wanted to get my coordinates of this vector v in terms of my blue bases here, my v1 and v2 vectors, I need to draw a perpendicular down to v1. So whatever this measurement is here, from here to here, that will be my first coordinate. And then my second coordinate I get by drawing a perpendicular down to my second basis vector. So the distance from here to here is going to be my second coordinate for v. I'm going to add 2 more lines to this drawing. First, I'm going to take this line here, and I'm going to move it so it's up here at this ending of this basis vector. So I'm just going to move a line parallel here, and then I'm going to draw one more line, which is to go from here to my vector v, because I want to have this box here. And you'll see in just a minute why I needed that. And I should note that this angle here is equal to theta, because this line here is just perpendicular to my x-axis, since this is the line I drew to get the coordinate, the y-coordinate of v. And then this line here is just perpendicular, well, to this line, which is perpendicular to this line. So the next thing I want to do is just label this angle from here to here also as theta. Because I'm going to mark more on this drawing, I made another copy just to make it more clear. Plus, I'm going to draw on this one, and then I'm going to make another copy and draw more. Okay, so the first triangle I want to look at is this triangle here that I'm highlighting in yellow. And the thing about this angle here, this is a right angle. And we know that because, how do we know that? Because this here is our first axis, and this here was how we drew our point from V. We drew a line perpendicular to our axes, and this line is parallel to this line, which means this angle is a right angle here, and we have our angle theta here, which now means we can determine the length of this leg of this triangle, yellow triangle, and the length of this leg of the yellow triangle. Remember, the height of this is v2, right? This gray line came when we were figuring out the coordinates of v with respect to our old bases. So this height here is v2, and then this is the side opposite of our angle. So this is v2 times the sine of theta, and this side is adjacent, so this side is v2 cosine of theta. I made another copy of this diagram here, and I highlighted this triangle, this yellow triangle, and we can see that this side, this little small piece of this side of triangle is v1 sine of theta, and this adjacent is v1, again v1 is my coordinate of v, v1 cosine of theta. Now I am ready to get my coordinates for v in terms of this v1 basis and this v2 basis. Remember, we wanted the length of this coordinate. We dropped our perpendiculars to v1 and our perpendicular to v2. So this length here is how far along v1 we want to go. So the length of this line is going to be our first coordinate, and the length of this line is going to be our second coordinate. So our first coordinate, v1 prime, is going to be the length of this, which is the length of this yellow line, v2 sine of theta, plus the length of this line, v1 cosine of theta. Now for v2, we want this small little area here, but that's simply going to be our entire line, v2 cosine of theta, minus this length here, which is v1 sine of theta. So here are our two equations that relate v1 prime to v1 and v2, and v2 prime to v1 and v2. Now we can see these equations, we can write this in matrix form, right? So v1 is equal to this row times this column, so we have v1 cosine theta plus v2 sine theta, which is this equation here. And our next v2 is this row times this column, so we have minus v1 sine theta, which is our second term here, plus v2 cosine theta. And that is exactly what we have here. We can take a vector in our unprimed system multiplied by the matrix and get the coordinates in the primed system. One last note, and you probably would not make this mistake, but I did. And that when I was trying to find my matrix, the first thing I wrote down was the matrix to rotate system. So in other words, taking a vector v, like it might be pointing this way, I wrote a matrix to rotate the vector by 45 degrees or whatever, however many degrees, which is not the same. This is not about rotating the vector. It's just about expressing the vector in a new coordinate system that is rotated. So the vector stays put. There's a new coordinate system. We just need the new coordinates of the system. So just remember, when you think rotation, sometimes your mind might go automatically to rotation matrix, but this is the matrix to convert coordinate systems where the coordinate system is rotated. Okay, so we did a lot of geometry to figure out this, but there's not always going to be like this nice little rotation. And so we need another way to find the transformation matrix. So again, we have our coordinate in some bases system, and we want the coordinate v, the vector, to be in a primed coordinate system. And A is going to be our matrix, our transformation matrix. So we're going to go over two methods for finding the transformation matrix for Cartesian systems. So don't do this, don't try doing this on the like spherical, to go from Cartesian to spherical. We'll cover that later. So the first method we're going to use is if you know the basis of both coordinate systems. And I'm going to show you two ways to do this. This way is from linear algebra, and I like it because it really, it's something that's going to be easy for you to remember because it makes sense. However, it's a much longer and more painful way than this over here, which is so super easy, and I feel really betrayed because I didn't know this earlier, and I always did it by this painful way. But maybe that's why I remember it so well. It was so painful. Anyway, let's do this first method. So just to remind ourselves, this first way is the slow way. And I'm going to use this example that we had when I introduced tensors. So we've seen this example before. And I also like this because this first example is a rotation by pi over 4. So later we can compare our results to what we got just a minute ago when we wrote our rotation, our matrix for the rotation. So anyway, this new coordinate system is the old basis rotated by pi over 4. So here is our standard bases. This is our new bases in blue, and we get it by rotating this old gray basis by pi over 4. And then just for an example later, we're going to use a vector, which is the vector 2, 3, this point here. We're going to represent this point 2, 3 in this new basis. And these green lines give you the hint that essentially what we need to do is take this point, drop a line perpendicular to our new blue basis vector, and then drop a line down perpendicular to our new second basis vector. To find our matrix, I first need to identify my old basis, which I said is going to be my standard basis, 1, 0, 0, 1. Our new basis, now, if we rotate by 45 degrees, we're going to go through the point 1, 1. So 1, 1 is definitely a point along our new basis line. However, 1, 1 is not a unit length. It has a length of square root of 2. So to make I want an orthonormal basis just because it's nicer to work with. My new basis, my 1, 0 basis rotates to 1, 1. So to normalize it, I divide by square root of 2. My basis here, my y-axis, which is 0, 1, it gets rotated by 45 degrees. So the coordinate negative 1, 1 is definitely there, but it also is not unit length, so I need to divide by square root of 2. So I have negative 1 square root of 2, 1 square root of 2. Now to make my transformation, I'm going to point to this formula here. I want to write my old bases as a linear combination of my new bases. In other words, I want my old bases, I don't know why I did 0, 1 first here, as a linear combination of my new bases. And here I had 1, 0 as a linear combination of my new bases. And I did not just guess these coefficients. If you remember from linear algebra, what we need to do is solve the augmented matrix. And if you don't remember, I'll refresh your memory right here. So I have 1, 0, my first bases vector, and I want to write it as a linear combination of my new bases. So I want to have x1, some scalar coefficient multiplying my first bases vector, 1 square root of 2, and 1 over square root of 2, plus another scalar coefficient in front of my second bases vector, which is my minus 1 over square root of 2 and 1 square root of 2. So what I'm trying to solve is this system. I take my first vector, my second vector, and then my solution vector. This is my augmented matrix. And then I'm going to row reduce this until I get something in echelon form, which is the staircase. So the first thing I did is I multiplied both lines by square root of 2, just because I don't like working with fractions. So I have a 1 minus 1 and then square root of 2, a 1, 1, and a 0. And then I subtract the second row from the first column because that will give me a 0 here. So I get 1 minus 1 is 0, minus 1 is minus 2, and then square root of 2 minus 0 is square root of 2. So this here, this column represents x1, this column represents x2. So this tells me that minus 2x2 is equal to the square root of 2, which means x2 is equal to minus square root of 2 over 2. And this line tells me that x1 minus x2 is equal to square root of 2, which means that x1 is equal to square root of 2 over 2. So these are my two coefficients. That means 1, 0 is equal to my first coefficient is square root of 2 over 2 times my first basis vector. My second coefficient is minus square root of 2 over 2 times my second basis vector. And you can multiply this out and you can verify that you're going to get 1, 0, right? If I multiply this out on the top row, I get 1 half. Over here I get 1 half, so I get 1 on the top. This is 1 half minus 1 half, so I get 0 on the bottom. I do something similar for 0, 1. I set x1 times my first basis vector, x2 times my second basis vector. I write out my augmented matrix, which is my vectors here with my solution. I multiply it by everything by square root of 2 because I don't like working with fractions or square roots. And then this is the resulting matrix, and then I subtract the second row from the first row. I have my equations, and I get that x1 is equal to square root of 2, and x2 is equal to square root of 2. So that's this linear combination here, and you can verify that I have the correct answer. This means now that 1, 0, the coordinates of my 1, 0 vector in my new bases, the coordinates is equal to square root of 2 over 2 and minus square root of 2 over 2. The coordinates of my vector 0, 1 and my new bases is square root of 2 over 2 and square root of 2 over 2. This matrix, by the way, if I multiply this square root of 2 over 2 by square root of 2 over square root of 2, I get this first coordinate is equal to 1 over square root of 2. Multiplying the second coordinate by square root of 2 over square root of 2, I get the second coordinate is minus 1 over square root of 2. Similarly here, I'm going to get 1 over square root of 2, 1 over square root of 2. So I can write my matrix now. So my matrix is simply this coordinate here, 1 over square root of 2 minus 1 over square root of 2, and this coordinate here, which is 1 over square root of 2, 1 over square root of 2. And that will convert my x1, x2 vector into my x1 prime, x2 prime. In other words, to get this transformation matrix here for each of my old basis vectors, here is my old basis vectors, I find its coordinates with respect to the new bases. So here I found the coordinates, these coefficients. And these coordinate vectors then, these two, become the column vectors of my transformation matrix. And remember, this is the slow way, but it's something that's easy for me to remember because once you know how to transform the bases, you know how to transform any vector because any vector is a linear combination of your bases. And then you can also just choose this matrix. But as I mentioned, there's a fast way to do this, and who doesn't want that? And here is the formula for our easy way. It's just this dot product. But let's look and see how we get to this formula. We're going to start with this statement here. We're going to say that there is some transformation matrix that'll take us from an unprimed coordinate system to a primed coordinate system. So again, A sub ij is our transformation matrix. Then here we're going to have a vector v, and we're going to say we can express it in our unprimed coordinate system as, a linear combination of its basis vectors, v sub k being the coordinates or the scalar multiples of our basis vectors. Or we can write it as a linear combination of our primed basis vectors. But this vector they're going to be equal. So they're two different expressions in two different coordinate systems, but the vector is going to be equal. The next thing we're going to do is we're going to take this equation here, but we're going to substitute for our primed coordinates, we're going to substitute our unprimed coordinate times our transformation matrix. So for v sub I prime, we're going to substitute a sub ij, v sub j, right here. Same equation, v sub k times e sub k, a sub I, j, v sub j times e sub I hat prime. This last statement here is true for any vector vk, so we're going to say it's true for em, where em is one of the other unprimed basis vectors. So we plug in em into this equation. Over on this side, this is pretty straightforward. A sub ij, v sub j is equal to em, e sub I hat. And over here, we're going to have our v sub k is equal to em. So when we multiply em times ek, because these are orthonormal, if k does not equal to m, then it's going to be equal to 0. And if k and m are equal, then we have 1. So we're going to be left with our vector em on this side, on the left-hand side. Next, we're going to look at this em and ei. So, we're going to look at the matrix A sub ij and the em. So if we have a matrix A sub ij, and I just kind of wrote out a 3 by 3 here, and we multiply by em, let's say m is equal to 1. So let's say it's 1, 0, 0. What you notice is our first basis vector is going to pick out the first column. Similarly, our second basis, E2, will pick out our second column. So EM is going to pick out our mth column of this matrix, which is how I went from A sub ij to A sub im times EI prime hat. I'm going to dot both sides of my equation with En prime. So En prime dotted with Em equals AIM, En prime dotted with EI prime. Now this En dotted with EI, that gives me my Kronecker delta Ni, which then I can simplify with this AIM, which means my I can now be replaced with an N, so I get En prime dotted with Am, Em is equal to ANM. That means the ANM component of my matrix is equal to En prime in our primed bases dotted with Em being in our unprimed bases. So this formula here is the one written up here and also in our overview sheet. And we can also write this formula in index notation, which is written over here where I'm circling. So let's go back to our example where we had our standard bases and then we rotated by 45 degrees to get this new bases here. So here we have our old bases, our new bases. So A11, that's the first element of our matrix, which before we calculated as 1 over square root of 2, should be E1 prime, which is 1 square root of 2, 1 square root of 2, dotted with E1, which is 1, 0. So you see when we dot it, we get 1 over square root of 2, which is what we had last time. Our A12, that's going to be our E1 prime, so that's 1 over square root of 2, 1 over square root of 2, dotted with E2, which is 0, 1, which again is 1 over square root of 2. So A12, first row, second column, that agrees with our previous result. You can see A21 and A2 also agrees with our previous result. Now we can compare this to when we first, the very first example we did where we calculated this matrix for rotations. So if we had our standard bases and we rotated by a theta, theta degrees or radians, whatever it is, by theta, we had this matrix here. And so if we plug in, here we had pi over 4 in this first tensor example. So if we plug in pi over 4, we'll get columns cosine pi over 4 minus sine pi over 4. And the second column being sine pi over 4, cosine pi over 4. So if you evaluate this, you get the same matrix, which is, it's kind of nice. And then last, I never actually calculated this point 2, 3 as new coordinates in our new basis vector, so I can multiply my transformation matrix by 2, 3, and I get 5 over square root of 2, 1 over square root of 2, which, 5 over square root of 2 is what, a little over 3, so yeah, this is a little over 3 here, and square root of 2 over 2, so square root of 2 is like 1.7, so like 1.4, so then divided by 2, we should get 0.7, so yeah, maybe this is about a seventh. So now we've looked at determining our bases. When we know the bases for both coordinate systems, we can do this a slow way, or we can do this a new fast way. So next, well, what if we don't know the bases of both our coordinate systems, but we do know some relations between the two systems? So this is our formula that we'll use. We'll derive it, and then we'll come back to our familiar example and use these formulas to derive the same matrix. We start with dr, where r is our position vector, so r is our x of I coordinate times our ith basis vector. We can have another coordinate system now, where we have our x of I prime coordinate times our e sub I prime basis vector. I also expanded these two sides out. Here I expanded this first side, here I expanded the second side, just in terms of our index. So I expanded our indices. Anyway, the next thing we have is we have a relationship between x of I prime and our x1, x2, x3 in our unprimed system. So in other words, we know what the relationship is between our prime system coordinates and our unprimed system coordinates. It's given to us here. So if I plug this in, my dx of I can think of x of 1 prime as a function of x1, x2, x3, where x1, x2, x3 are the coordinates in the unprimed system. Similarly, x2 is a function of x1, x2, x3, where these are the coordinates in our unprimed system, and x3 prime is a function of our 3 coordinates of our unprimed system. Expanding our derivative of x1 prime, we will take the derivative then with respect to our first variable x1, our second variable x2, and again this is x2 in the unprimed system, and then our third variable x3. Again, x3 is in the unprimed system. And just kind of writing this in index notation, so the derivative d x of I prime is partial derivative of x of I prime, x1, x2, x3 with respect to the first variable x1 dx1, or x2 dx2, or x3 dx3. And when we look at this derivative is equal to a sub ij, the derivative of x of j, which means that a sub ij, our matrix element, is equal to the derivative of x of I prime with respect to x of j. So here's our formula that we're going to use. We're going to do it in an example. And here is our rotated coordinate system example again. And we've already come up with the matrix. And we're going to use this matrix to verify our answer, compare the answer that we get using this formula here. And the idea here again is that our primed system is a function of our unprimed system coordinates. So the idea is that now we're given this relationship here, that v1 prime is a function of our unprimed coordinates v1 and v2, and v2 prime is a function of our unprimed coordinates v1 and v2. So what I'm trying to tell you is this relationship here should be given to you if we want to use this method here. And just to write these expressions, at least for V1, in terms of our method or these formulas over here. So V1 is a function of V1 and V2, our unprimed coordinates. And that function of V1 and V2 is cosine theta V1 plus sine theta V2. So at this point, really, your theta, because you know your angle of rotation, cosine theta and sine theta, they're like coefficients, right? But V1 and V2. So our x1 and x2, our unprimed system, is V1 and V2. Our x1 prime and our x2 prime system, our primed system, is V1 prime and V2 prime. That, again, is to put it in these terms here. And now we're ready to use our formula. So let's look at dv1 prime here. And that's going to be dv1 prime, and we put in our function. So our function of v1 is cosine theta v1 plus sine theta v2, and we're going to take the partial derivative with respect to v1. And then we're going to add that to dv1 again, which is cosine theta v1 plus sine theta v2, and then we'll take the partial derivative with respect to v2. So I'm using this formula here. And there's only two variables, so we're only going from dv1 to dv2. So the partial derivative of cosine theta v1 plus sine theta v2 with respect to v1 is simply cosine theta. The partial derivative of cosine theta v1 plus sine theta v2 with respect to v2 is simply sine theta. I do the same calculation for v2. At this point, the function of dv2 is minus sine theta v1 plus cosine theta v2. So I write that in. I take the partial derivative with respect to v1 and then partial derivative with respect to v2. So partial derivative with respect to v1 is minus sine theta, and partial derivative with respect to v2 is cosine theta. So now what I have is this equation here. And I have a sub ix dx. And so I just need to single out my a sub ix. So I have my cosine theta for my 1, 1 term, my sine theta for my first row second column term, my minus sine theta for my 2, 1 term, second row first column, and for 2, 2, I have cosine theta. So it's the same matrix. And again, we use the system because we were given not so much that we have this rotation, it's that we were given this information here. We were given information, I should put it in green. We were given this information here. It's up here, you know, it's this information. We're given a formula for the primed system in terms of the unprimed system. The last topic we'll talk about is the inverse. I'm going to go through the derivation of this conclusion here, but I'm going to cut to the chase now in case you don't want to hear all of this other stuff, how we derived it. This is our last topic, so you can skip it. After you hear that, the matrix, our transformation matrix A times its transpose, this little dagger that looks like a T is transpose, is equal to 1, which means the transpose is the inverse. So if we have an orthonormal, so this is the big thing, if we have an orthonormal basis and we're in Cartesian coordinate system, it's super easy to get the inverse, where instead of going from our unprimed to our primed, we can go from primed to our unprimed coordinate system. So if the original and the primed coordinate systems are orthonormal, the inverse transformation is the transpose. Super duper easy. This is why we like Gram-Schmidt. If you don't have an orthonormal basis, you use Gram-Schmidt from linear algebra to get one. And of course, it's even better now that you're not in linear algebra because you can use a software package or you can use something else to do the Gram-Schmidt for you. We start this derivation of this the same way we did when we were looking at how to determine our matrix from basis vectors. We say that first we have our unprimed system, our prime system, and there's a transformation to go between the two. We say that a vector v can be represented in our unprimed system or our primed system, but it'll be the same vector. Different representation, same vector. And then we say, okay, we're going to plug in our transformation matrix times our unprimed system in for our v sub I prime. So for v sub I prime, we plug in this a sub ij, v sub j. And we say this is true, the statement is true for any vector. In particular, it's true for em, one of our unprimed basis vectors. So we multiply on this side because ek, if k and m are not equal, it's going to be equal to 0 because they're orthogonal basis vectors. So if they're perpendicular, they're going to go to 0. And if it's the same, we're going to be left with em on this side. Here we have our a sub ij, our em, our e sub I prime. And then our em will pick out the mth column of our a sub I matrix. So we have em is equal to aim e sub I. And then what else did we do? Oh, so then for some reason in our book, instead of em, we switched to ej. So ej is equal to a sub ij, e to the I, this should be prime probably. We dot both sides of our equation by an e sub k, and this should be prime. And then what we have is here, we're going to have the Kronecker delta is equal to a sub ij, and here we're going to have a sub ik. And this is because this is a unit vector, so we're okay with a sub ik. And that means this Kronecker delta is our identity matrix is equal to A. And then this, we're claiming a sub ik is our A transpose. So now what we have is that our original unprimed coordinate systems are orthonormal. The inverse transformation is the transpose. We can write this, so A inverse A equals 1, and in index notation we can rewrite that here. And then we see that the transformation matrices which obey orthonormal conditions are simple to invert. That A inverse is equal to A transpose, and in subscript notation we can write it A sub ij inverse is equal to A sub ji, or Vi is equal to A sub ij V sub j prime. To review what we covered in this video, we looked at transformations between Cartesian coordinate systems, and we looked in particular at vectors. We are going to generalize this later to tensors, so not just vectors, but matrices which satisfy the tensor definition, as well as arrays of matrices and arrays and arrays of matrices. So the first thing we did is we looked at a vector transformation between Cartesian systems, and the first transformation we looked at is actually it's the only one we kept using the same example. We took the standard basis and we rotated it by an angle of theta, and we looked geometrically at what the matrix transformation would be, and this is the matrix we got to go from our old bases and our standard bases in black to our new bases, our coordinates in this bases in blue. The next thing we did is said, well, we'll need to be able to find the transformation matrix, not always using geometry. So we had two methods. The first is if we knew the bases of both coordinate systems, and the slow way to do this is to write our old bases as coordinates in their new bases, and then using those coordinate vectors as the column vectors of our transformation matrix. And then we found a second way that was much quicker, that no one told me about, like all this time I've been doing it the slow way, but we found this easier way. So our transformation matrix, if that's A, then our m row nth column entry is going to be en prime, so the nth basis vector in the primed system dotted with the em vector, the mth basis vector in our unprimed system. And we did examples here. And then the next way we found a transformation matrix, if we didn't know the bases for both, but we knew coordinate equations relating the two systems, such as this information here, we have V1 written in terms of V1 and V2, and our second coordinate is given to us in terms of V1 and V2. We found these formulas here would give us the transformation matrix. And the final thing we looked at is if we have orthonormal basis vectors, and we're in the Cartesian coordinate system, it turns out that the inverse matrix to go the other way, from the primed system to the unprimed system, is simply the transpose of the transformation matrix. So it's a very simple way to do the opposite, the inverse matrix. Okay, so that was it for this video. Thank you for watching.